for a lot of things I'm going to talk about now. So the title of the talk is Privacy and Fairness in Collaborative AI, but more specifically, I'll be talking about federated learning, which is work I've been doing during my postdoc with Salman Avesmer at USC. So following up on the talk by Flavio and talk in the morning, the idea is that we have nowadays a lot of data generated that is very close to who we are. So it's with our interactions with the environment, either our biological interactions or talking with people, things that we do in our life and so on. And with this huge amount of data, it's very useful for machine learning models, but it also brings to the limelight the issue of trustworthiness, which is a big part of this workshop. And trustworthiness, we can look at it, the theme has been throughout the last couple of days. There's one side of privacy, let's say yesterday, and also today there's been a lot of talks on fairness in machine learning models. So in order to be able to access and make use of these data, we need to have some sort of guarantees on data privacy and group fairness, as we have alluded to. So one way to access data that users have that has been recently proposed in the community, I mean, not recently, it's been a big chunk of years, but which is federated learning. And the idea is that instead of centralizing data access, we actually leave the ownership of the data to the users, and we want to train a machine learning model using some parameter server. So the users train the model locally, and then we aggregate these local model updates at the server and keep repeating that. And in this way, we're refining the model training. Now, after this initial proposition, it's come in a lot of different papers, issues with just sending model updates. Is that not sending data and just sending gradients, for example, is not necessarily enough to protect the data privacy. For example, using gradient, you can easily reconstruct images that have been used in the training. So there's need for doing something more. So we need to have some privacy guarantees. Otherwise, users are a little bit reluctant to share their information. Also, we can face some legal roadblocks to that. But we can also, if we bring into the equation also fairness, not sharing features is one thing, but you will be even more protective of sharing the sensitive attributes that define you as an individual. And if we somehow pay in terms of performance to avoid sharing this information, then the penalty that we get in critical applications such as healthcare or credit scoring or hireability, as was alluded to in previous talks, is a huge consequence. So in this talk, I'll be looking at particularly two sides of this trifecta. In particular, we're looking first at privacy from the point of view not of differential privacy, but rather using the secure aggregation algorithm. And we'll be presenting some guarantees for what we can actually kind of protect using secure aggregation. And then we'll be building on that. We'll be using secure aggregation to actually present a model for training group fairness, training a group fair model in a federated learning setting. So without having access to the data, how can we make sure that the model trained is fair, even when the distributions across clients are very heterogeneous? Okay, so the first part of the talk is on these privacy guarantees, and this is work that is soon to appear, I think, in July in POPETS. And just to set the stage, we'll be particularly talking about information-theoretic privacy, where the privacy violation is measured by the mutual information between what the data is and what is actually revealed into the system. So the benefit of approaches that target information-theoretic privacy is that you do not get a penalty to the end-to-end performance, but this comes at a cost to a huge cost usually to the system efficiency. On the current part, there's differential privacy, where you randomize the output in order to make the output distribution close multiplicatively for neighboring inputs. And this is a worst case protection. It's definitely more robust to auxiliary information, but it comes at a cost to the end-to-end performance. So this will be the focus today. And typically, the most famous approach to give such guarantees is the use of secure aggregation, which is secure multi-part computation protocol. So the idea is you start with the latest global model, you compute the local updates, and then these local updates are typically computed using, for example, if you use Federated, then you sample a batch of data points, compute the gradient on it, and this is how you compute the update. And then we would like to send these to the server so that the server can compute the average of these updates. What you typically do is instead of sending the XIs in the wild, you would encrypt them using secure aggregation. And one way to do that is the clients would exchange a pairwise seed and then use the seed to generate noise that is common across every pair. One client would add the noise, the other would subtract the noise, and this is done in the finite field domain. So the idea is looking at any of the n-1 users, whatever is being sent looks completely uniform, but once you complete the missing piece, then you are able to compute the sum that you would like. So the guarantee that we get in this case is can be expressed in terms of mutual information as following, is that conditioned on knowing the sum or the average, the mutual information between whatever the users have and whatever is being sent in the system is equal to 0. So there's no leakage in this sense. But the server still gets access to the average model or the aggregate model. And the question is, how much does the aggregate model leak about the client's data? So this is what we'll particularly be talking about in this part of the talk. And we ask this question in an expanded way in 3 different facets. One is, how do you quantify the leakage, and how is the leakage affected by the system parameters, and is this actually a good representative metric? So for the first 2, we give some theoretical guarantees, and we verify these experimentally. And for the last one, we demonstrated experimentally by comparing our measurements with model inversion attacks. Okay, so let me get to the results. So the main central result that we have is the following. It is a bound on the amount of on the mutual information between any individual update and the aggregate model that the server computes. And this is done for the Federated protocol. So this upper bound is actually a function of multiple system parameters. In particular, the ones of huge interest are the number of clients that we have in the system, which is characterized here by n, the model size, and the local batch size. So as you can see, as the size of the model increases, you actually leak more information because the model can actually remember more information about your data. As the number of clients increase, the first term, decreases like 1/n with the number of clients, and this term log n/n-1 is actually also upper bounded by order 1/n. So the last term that's remaining is the C, and this bound is under a particular set of assumptions. In particular, assume that the data is sampled across the clients in ID fashion. And the other is the fact that we assume that the sample stochastic gradient has a sigma log concave distribution. This assumption is not necessary. What's most important is IID. So if you discard the second assumption, you're going to get the second term, but this first term, all you can argue is that it's something that decays with n. So this is what we have for a single round leakage, and the beautiful thing is that you can extend this guarantee using chain rule into a multi-round leakage guarantee, where you get a linear scaling with the number of training rounds. It's been shown yesterday that, I mean, in terms of differential privacy, this is not necessarily something that you do not necessarily have a linear leakage. This is the current bound that we have, but we'll show through experiments that it's not also linear in terms of mutual information. Okay, so this is the main bounds that we have for the leakage. Now, how does this compare experimentally? So in order to do this, we compared it on 2 pretty small data sets, the MNIST and the Cypher-10. And the reason for that is that in order to actually measure mutual information, we have to run, we use the mutual information neural estimator. And to do that, you have to run an experiment multiple times. And then these represent samples that are then fed to that estimator to compute the mutual information. So the first column represents the part of the experiment that aligns with our theory. And in particular, here we're using the Fed SGD protocol. And you can see that as the number of users increase, the leakage that you get decays with like order 1/n. We see very similar trends when we use the Fed averaging protocol or FedProx, which is just some form of regularization of Fed average. The second thing that I want to highlight here is that how this metric
So if you go back a previous slide, you know, the second term log1, it's really scaling linearly with D and T, right?
Yeah.
So are you assuming that the number of users way more than the millions of parameters? Is D like a local model or the global model?
It's the same size.
Oh, it's the same size. Okay. I mean, this bound it could be vacuous, but on the next slide.
Oh, this is so very clear. This is for single round leakage.
Okay.
Right. So this does not take into account T.
Okay.
Right. I'll be showing how T.
So where's D here? Oh, is
so
that
D is kind of a different model. So this one, the first one is logistic regression model. The other is single layer perceptron and then multiple layer perceptron.
Okay, so we're about 1,000.
Yeah. It's not like it's not like a ResNet model. But
No, but then so normalized, you're just divided by the entropy.
Yes, it's kind of like a fixed. I mean, I can report what it is in bits, but then it's not necessarily descriptive from one data set to the other. So what we decide to choose is just to compute the entropy of the data set and the entropy of one client's data set. Again, using something like the mutual reference. So this is So here we are plotting two figures at the same time. One is the estimated mutual information leakage, and the other is the success of the modeling of gradient inversion attack. In particular, we are using peak signal noise ratio to evaluate its performance, but you can also look at it qualitatively by saying that the image is actually the reconstructed image is becoming worse and worse as the number of clients in the system are increasing. Okay. Now, the last thing that I want to discuss in this part is how does the privacy in the model, how does the privacy and the accuracy change as you run the experiment? So this is measuring the accumulative leakage. In particular, we are looking at the leakage after a particular number of rounds. So you can follow this trace, basically saying that we start with this particular model accuracy after one round, and this is the leakage that we have, and then this is following this. This is how the leakage and the model accuracy evolve. So you can see that at the in the very early rounds, the model accuracy is growing pretty fast, and the leakage is growing kind of linearly with it. And then after that, the model accuracy kind of plateaus, and the leakage is still increasing monotonically, but it's at some training grounds, the leakage is not growing linearly. So the takeaway that we want to say here is that as you train more and more, you're actually leaking more information, not necessarily in a linear fashion, but you have to make a conscious choice about when to stop, because you see here even in both data sets, after this particular stage, you're just gaining very small in terms of accuracy, in terms of percentages, but the leakage has been almost tripled. Yeah, has almost tripled. So it's kind of a design choice about when do you stop the training, right? So this is kind of the first part of the talk that I want to highlight some of the results we have in terms. Yeah.
So is this accumulated leakage? So how does it go down? No.
Where?
No, I think
This one?
No, I think I'm. Yeah, so I think that like if you go to the left a little.
Oh, that weird point there.
Yeah.
This one?
It's noisy there.
No, actually, it's just increasing.
It is going up.
I haven't had coffee.
I guess it was one of the ones where the accuracy dropped a little.
Yeah.
But yeah, it happens. Maybe you should run more seeds, man. I don't. So I'm going to assume you're not doing any DP right now. This is just sending a raw model with secure aggregation.
No, we're not doing any DP. We're not doing any DP. Yeah, but so it's kind of interesting to see that, okay, the guarantees that you can get using secure aggregation. So, okay, so I have to be very clear. You cannot give guarantees, you cannot give differential privacy guarantees using all secure aggregation. It's very easy to construct examples where it breaks, right? But you can also think of the other users in the system as if you're inducing noise to your own protection. And it is kind of an open thought question about whether you don't necessarily need to add noise everywhere in the space of the model. You might want to just add noise in places where, let's say, the subspace where you do not get any protection from the other users. But as of now, we're not really looking at DP at all. Okay, so the second part will be talking about how to train group fair models and using federated learning, and in particular, we'll be relying on secure aggregation a lot here in our computations. So the first part, I'll run through it because Flavio gave a very nice introduction to it. In particular, we are targeting training a globally fair model in terms of group fairness. And there are multiple ways of looking at it: equal distribution or equal performance, and multiple metrics to evaluate both of them. So in equal performance, you want to equate the true positive rates, whereas in something like equal distribution, you'd like to just look at the model at the output distribution. Okay, and there are a lot of ways to target this bias that you have in training through that can be basically categorized into three main methods: pre-processing, in-processing, post-processing, as Flavia described like a few minutes earlier. But let me now get to the challenges of trying to do fair training in federated learning. In particular, the main challenge that you will face right away is the fact that the distribution that you are targeting to be fair with respect to, which is a global distribution, is actually divided across the different clients. And each of these different clients might not have a representative distribution of the global distribution. So one example of that is if you look at data from the census, then you see that different race distributions across. First time I presented this, I had some challenge with naming the state. So this is Maine, and then the state on the top right, and then in California you see a different race distribution, and also different number of representative points in each of the clients. So what this would lead you to believe is that local debiasing cannot necessarily guarantee global fairness, and we can actually create some toy examples to test this out. So we took one famous data set, the other data set that Flavio is talking about, and partition it into different silos. And you can see that if you are in the homogeneous case, then so the blue bar is basically representing the performance of federated averaging, where you're running without any care about fairness. The orange bar is representing local reweighting, where you're applying a debiasing method, but you're applying it on the local data set. And in the homogeneous case, this is pretty good because it's a representative yet noisy sample of the full data set. But as you go to more heterogeneous settings, the performance degrades. And just to show a representation, this is what the accuracy drops like, but you can see that the range is not necessarily very bad. Okay, so local fairness does not imply global fairness. This is the takeaway, and the question that we want to go after is how do we go about solving, right? So we present an algorithm to do that. It's interesting. It's still an interesting problem. What kind of theoretical guarantees can we put on it? But this is how our intuition to solve this goes. So in federated learning, we'd like to solve an objective function that looks like this. And typically, you weight the local losses that you have across the clients by the number of data points that these clients have. And the idea that we have is that we would like to apply local debiasing in order to preserve the privacy, because we do not want to share any information about what the data sets look like with the server. But since local debiasing is only addressing the local view of fairness, which can be different from the global view, we would like to favor the clients whose local fairness metrics are close to the global fairness metric. So how do you find the global fairness metrics? This is a reminder of the previous slides. I'll be using EOD, the equal opportunity difference, as an example throughout the rest of the talk. But on binary data set, on binary decision data sets, you define it as the true positive rate for group 0, minus the true positive rate for group 1. And if you want to apply this locally, you basically just extend the definition by only looking at the data set at client K. Okay, so normally, if you get the following updates after one round of training, then if you apply federated averaging, then you would get a point that looks like this. Now, the main idea that we are presenting here is that we would also like to view how these models are looking on the fairness plane. In particular, you can look at any fairness metric as a linear projection from the model outputs. So let's say that this is the projection that you should have gotten from the global view. So this is the global metric. And each of the clients have a local view F1, F2, and F3, assuming 3 clients here. Then what you would do is you would increase the weights in the aggregation for clients 1 and 2, because they have very similar projections or very close projections to the global view. And you would decrease the weight of F3 because it's very far away from your global projection. So doing something like that will lead you towards a model that is a little bit geared towards X1 and X2 because they have higher weights in the aggregation. Okay, so how do we do that in the algorithm? Well, the first thing that we do is the server and the clients collaboratively compute how far each of the clients are from the global view. So using this difference delta K. And then for clients that are higher than the average, we increase their weights. For clients that are lower than the average, we decrease their weights. And we normalize and repeat this in every cycle of the training. Now, one important thing to highlight here is that here we're assuming that we are able to compute what the global metric looks like. So how do we do that? So the global metric, we can actually rewrite it in terms of, we can take the true positive rate difference and rewrite it in the following form. Just checking that it's there. Okay, and basically you can see here that this part of the expression is actually a local information that each of the clients can compute, whereas these green parts are global data set statistics. So for example, if you're looking at a healthcare application, this is basically saying the percentage of individuals in the data set that have disease X from group A. This is the number of points at this particular client divided by the total number of points. So, okay, so since this is local information and this is a global data set statistic that is known, or you can, if you want, you can compute it before training using an invocation of the secure aggregation protocol, then each of these terms can actually be computed locally by client K, and then you just aggregate this using secure aggregation to get the global fairness metric in every training round. So with this, we can just describe what the algorithm looks like in every round. In every round, each client trains locally and applies its own local debiasing. And then the server computes a global metric using the equation that we described in the previous slide by using the secure aggregation protocol, and then broadcasts this to the client. And then each of the clients with the server will do another round of secure aggregation to compute the aggregation weights. And finally, we multiply, each client will weigh its model updates by that, and will weigh its model updates by that. And then the server will collect it into the new global model using secure aggregation. Okay, so how does this algorithm perform? We first tested on 2 data sets, the adult and the compass data set. And it shows that it works pretty well. In particular, we see that's resilient in terms of when we look at different heterogeneity levels. Just to explain here how we are creating these heterogeneous distributions, we're using the Dirichlet distribution to divide the points into different silos. And as the alpha becomes smaller, the data sets become more heterogeneous. And the particular parameter that we divide by is actually the sensitive attribute that we're looking at. Okay, so this is how it looks like in terms of fairness. But we can also see when we compare it, its privacy penalty, that we are getting very good reductions in the fairness metric with very limited penalties on the accuracy performance. This is the performance on menu partition dataset, but we also looked at datasets that are more naturally partitioned. Particularly looked at this ACS income dataset, which has like 1,600,000 data points, where naturally here you take each state as your client, so you end up with 51 clients. And we showed that you can still get very good equal opportunity reduction when training using our fair federated averaging algorithm. So I think I'm just about at time. So the conclusion that I want to leave you with is that secure aggregation allows you to hide information. It doesn't allow you to hide clients. So if you're looking to infer whether a client is in a system or not, this is not the protocol to do it. You're assuming that other users are helping you in that protection using their updates that they inject, which you can, in our analysis, you can treat them basically as the noise to your own update. And then you can use secure aggregation by invoking it in different stages to train fair machine learning models. The good thing about our protocol is that it does not necessarily enforce a particular debiasing method that the clients need to use. So each client can actually have, some clients can have no debiasing at all. Some clients can have reweighting. Some clients have another different debiasing method. We showed experiments here only on reweighting, but if you go to the paper, you'll see a lot of other interesting ablation studies. And this is what I want to say about secure aggregation. I don't want to leave, back to Lita's question, secure aggregation is not the all protection. And I just want to leave like one slide to highlight that, is that it is assuming a very big level of trust. So it's assuming that the server is only curious. It doesn't necessarily do any particular issues. It doesn't try to modify the training in any way. And one of the very great things about DP is that it's very resilient to auxiliary information. But that is not the only thing that the client can exploit. So for example, you can actually induce some model discrepancy in the training, and that can leak information in a catastrophic way. So again, I don't want to destroy everything that I built throughout the paper, throughout the talk, but just want to highlight the limitation that want to be fair. So the idea here is that it's going to be like two more slides, but the idea is that if the server is not sending the same global model to all clients, let's say that each client starts with X1, X2, and Xn. Here I'm putting them with different colors because they're different. Then you can actually leak information in a very bad way. And there is a very nice toy model that we came up with that does that. So the idea is the following, is that you can actually take the original model and just add to it like a prefix of your own design. And that prefix will be different across different clients. So you put 2 linear layers, and then you add a set of convolutional layers. But these convolutional layers are the only thing that is differing. So client number 1 gets this green part, and everything here is 0 plus these layers. Client number 2 gets the blue part non-zero, and everything else is 0 plus these layers. And when you do that, when the clients do backpropagation and they compute the gradients, you can design the weights in the fully connected layer and the convolution layer such that the images appear very clearly inside the gradient updates. And when you aggregate them, since this part for client 1 will only have non-zero updates, this part for client 2 will only have non-zero updates, and so on and so forth. Then when you aggregate them together, each client's data will appear very disjointly from each other. And we show that you can actually reconstruct it in a very crazy manner. Like this is not really trying to apply any generative model to recreate the images. You just take the gradients that you get, divide them by a constant, and you're able to recreate like 81% of the data points with the model trained on. So this is a very recent paper that we put on archive. Yeah, it's saying secure aggregation is private, but it's only private if you really have very great trust in what the server is doing. With that, I'd like to conclude my talk, and hopefully I didn't go over time.
Global fairness problem. Do you also encounter scenarios where the local fairness is like global fairness is achieved, but local fairness is not going down?
There will be, especially in the heterogeneous case, there will be some clients where that happens. Like most of the clients will have a low local fairness, but there will be one or two clients whose local fairness is very far away from the global, especially in heterogeneous.
The other question I have is here, sometimes these clients don't respond in federated learning, like so.
Yeah, that's we haven't really. So what we're considering now is so to be very clear, we're considering the silo setting. So each client is able to compute even what you call a local fairness metric. Right? If the client is just one individual with one particular sensitive attribute, then the definition of local fairness at that point really breaks, right? So in a silo setting, you're kind of assuming that everyone is going to be responding. It's not like a random access kind of setting.
So have you thought about computing F global in a federated way itself?
Yeah, that's, I think. So I mean, so the central thing that we're trying to do here is that make sure that everything, whatever you're computing, it is computed inside or encapsulated by the secure aggregation protocol. So here, in order to compute F global, you are relying on some local updates that the clients are doing, and then you're aggregating this. You're relying on local computations the clients are doing, and then you're aggregating that to get F global.
So I think to piggyback on the previous question. So if some clients are only updating, and then a client only has a limited batch size. Mm-hmm. I think you may be able to still create unbiased estimators for the local information, and then over time it should average itself out.
I see. What do you mean by over time?
So the clients are going to participate in multiple rounds, and every time there is a batch of their data that you're going to see, and then so you may be able to still get convergence guarantees. Similar to federated averaging, like federated.
But aren't you assuming that case that the model is not changing across these different? No, like because the global fairness is defined in terms of the current particular model, right?
Yeah, let's take that as fine.
Okay, thank you so much. The poster session now upstairs. Because we have a break from the poster session upstairs. There should be cookies and coffee up there. One other thing I wanted to say is, so again, the poster session goes until 5:30, but the building is locked at 5. So if you leave, you can't get back in. Also, the door to the second floor is locked.